In this video lecture, I will analyze Root-Locus behavior of a digital control system, specifically a system, under different sampling time conditions. Okay, so we have a plan, which is a simple first order plan, as you can see, 1 over s plus 1, okay, A0 to hold. And we have a controller, which is a PI controller, not technically a nice controller, but we are analyzing from the perspective of Root-Locus anyway. And the idea is testing or like analyzing the Root-Locus behavior of this system for t is equal to 0.5 seconds, t is equal to 1 second, t is equal to 2 seconds, and we will try to understand what changed or what doesn't change when we change the sampling time. Okay, so if we technically discretize the g of s and then later find the opponent transfer function, we will see that they are equal to this, like g0.5, g1, and g2. They are both transfer function. The order is same, and it should be the same because sampling time cannot change the order. The only difference is location of some of the poles, and the gains are different. Okay, the idea is we are using same gain. Okay, this is a discrete time gain, and the goal is understanding the closed loop poles, the change of closed loop strokes with respect to changing k. Okay, so what we'll do, we will technically can use the rules and procedures and draw the Root-Locus, but I did it for you using the method. Okay, so these are the Root-Locus, 0.5, 1, and 2. So initially, I want you to ignore all of the numbers and quantities on Root-Locus. Okay, so we know the unit circle, and let's try to figure out what changed when we change the sampling time. Okay, so if I increase sampling time, which means that I decrease my sampling frequency, which we assume that to be bad in general. Okay, we want to be as fast as possible, but as you can see, if you ignore the numbers, what's happening is qualitative little shape is same. Okay, so and there's a big circle in both cases, and the circle has the smallest radius for t is equal to 2 seconds, and it has biggest radius when t is equal to 0.5 seconds. From this perspective, you may assume that, okay, since a unit circle, the distance to unit circle in terms of radial distance defines the stability of the system, okay, and since this radius, okay, is much smaller than the radius here, you may assume that, okay, so t is equal to 2 seconds, which has the largest sampling time, which is lowest sampling frequency, provides the most stability, which is not correct. Okay, so this is if these were Root-Locus with the same sampling time. Okay, you will be correct because sampling time, if you just fix sampling time, you can just look at the ratios. It will give a convergence time in terms of the discrete samples. Then it will be okay. But the problem is for 2 seconds, in this case we have 1 sample. In this case, we have 2 samples. In this case, we have 4 samples. Okay, so if you look at the convergence speed or performance with respect to number of samples, of course, this can give a better information because we have less samples with the same amount of time. Okay, so this is another good idea, comparing different Root-Locuses if the sampling time is different. Okay, so we will look from different perspectives and analyze this. Okay, so one thing you should be looking at first is, what is the range of k values that makes the system stable? Okay, so obviously, when k is equal to 0, okay, k is equal to 0, all systems are marginally stable. They are not viable stable because we have a pole at z is equal to 1. Okay, so when we increase k, they all become stable because 2 poles here, as you can see, approach each other. Okay, they are stable, and at some point, the stability breaks down, and the system again becomes viable unstable after a large value of k. Okay, so what we can directly compare in terms of a general stability metric is the range of k values. As you can see, for t is equal to 2 seconds, k is 2.6. For t is equal to 1, it is 4.3. And for 0.5 seconds, it's equal to 8.2 approximately. So it means that the range of k values that makes the system stable is larger for t is equal to 0.5 seconds. Actually, if you remember for 302 nodes, this is the definition of gain margin. Okay, so how large you can choose k such that your system is still stable, and gain margin for this case is equal to 8, approximately 4 and 2. So from the stability robustness, gain margin, or range of stability point of view, of course, t is equal to 0.5 seconds is the best option. Okay, so this is the easiest way of comparing different root locuses in terms of stability. Okay, that's good. So now, okay, so we have a better range here. Okay, and I can pick more larger gains, which is good because in general, increasing larger gains increase your state performance, and having a better range is always good. So the second step is, what if I keep my K constant? Okay, and for example, 2. So for the same gain, how we can compare performances? Okay, so I will show you some results. Okay, so K is equal to 2. We are here. Okay. Okay, K is equal to 2 here. K is equal to 2 here. Okay, that's good. So now it's better to compare these results. Okay, before going to the quantitative analytical comparison, I will draw you the step response of the system. Okay, that's good. So this is 0.5, this is 0. No, it's wrong, it's 1, of course, and this is 2 seconds. Time sample time 2 seconds. And below, I plotted the actual time, not the sample index, okay, as you can see here, and these are the results. Okay, so what are the important transit performance metrics? Okay, if you remember, setting time, peak time, okay, percentage overshoot, and these are the important. We have also frequency oscillations. For now, just ignore the frequency oscillations. Okay, so in terms of overshoot, okay, t is equal to 2 seconds is 70%, which is really large, and actual overshoot, if you look at the continuous time system, is even higher because you will have a bigger overshoot here. In general, you have some sort of overshoot there. Okay, but sometimes weirdly, we have an overshoot difference here. So this is 40% and this is 48%. Okay, so it's kind of uncontracted that the middle one is the best overshoot, which is technically a little bit wrong because of the sampling time, we cannot exactly capture what's going on here. Okay, but still, it is obvious that the worst overshoot performance is happening with the largest sampling time or lowest sampling frequency. So in general, it's kind of hard to compare close numbers in discrete time systems, for example here, because of we technically slightly ignore what's happening between two sampling times. Okay, and even if we don't ignore that, sometimes you can get contracted results. But if there's a big difference, for example, 40 to 70, 48 to 70, and it means that this is worse. Okay, so and it is true that on average, not always. Okay, so overshoot, percentage overshoot. Okay, so let's have percentage overshoot. Overshoot T2 is larger than percentage overshoot T1 if T2 is larger than T1. And this is not an exact increase. This is an average increase. Okay, for all systems, if you look at the general behavior, you observe such a behavior. But if they are close to each other, then you can clearly say that it's kind of hard to comment on before simulating the results. Okay, good. And if you remember these formulas that we derived in H302, they were even approximate for the continuous time case. They are even more approximate crude in the discrete time case. Okay, so we are done with overshoot. Okay, so we get an idea. And let's look at the sampling time and rise time, peak time. Okay, so in the peak time, which is even clearer here, as you can see. So it is 2, 3, and 4 seconds. And this is correct. Okay, so peak time is kind of how fast we reach its peak value, which is an indication of the speed or the fastness of the system. And obviously, it is best when t is equal to 0.5 seconds. And this is also, of course, 1. This is 2 seconds. And for example, for a different system, you can get a similar result, okay, between 0.5 and 1 or 1 to 2. But similar to the overshoot, this is a general trend. You can expect to increase your overshoot or peak time if you increase your sampling time. Okay, so technically TP, SDP increases on, let's say that, okay, on average, you should expect that as T sampling time increases, if you keep everything the same, T peak should also increase. But of course, in order to talk about the peak time, the behavior should be oscillatory. It's also one of the limitations. Okay, so better metric where we can really compare the speed is the sampling time, which is valid for both underdamped, overdamped, like oscillatory non-standard systems. And as you can see, like 8, 9, and 8. Okay, good. So as you can see, they're close to each other. T is equal to 1 second has the largest settling time, and t is equal to 0.5 and 2 is similar. Okay. So again, because of the discrete time sampling, since we cannot capture inter-sample behaviors, it's almost impossible to compare close numbers. Okay, but it's obvious that they are close. There's only 1 second difference between these two and between these two, and overall we have the settling time in between 8 to 9 seconds. Okay, and this is true and technically, and I will show you why. In general, if you keep the sampling time fixed, okay, if you change sampling time by keeping everything the same, for this, for example, specific example, you should expect that these sampling times are approximately each other, okay, approximately equal to each other, and I will show you why in the next slide. Okay, so these are the results, as you can see, which means that in terms of transient performance, if I keep everything same, changing the sampling time and increasing the sampling time in general degrades the performance. But in the case of sampling time, it's not degrading the performance, right? It's approximately the same, but overshoot is increasing, peak time is increasing. They're both bad, but sampling time seems to be very close. Okay, so let's talk about this. So why overshoot is higher? It's very simple. Okay, so this is the phase, and if you remember, the frequency of oscillations are defined with the phase angle of the complex pole with respect to the positive real line. Okay, so this is here, this is like phi, this is phi, and this is phi. If you increase the frequency, or if you increase the angle, what you make is you make the system more oscillatory, and this is equivalent to like going diverging from the real line. And if you remember, if you diverge from the real line, you increase the overshoot, you decrease the damping, and it's the same thing. Okay, and if you remember, we technically, if you just map this line, okay, to the complex plane, it will be a circle inside the unit circle, and when you avoid from this, you will technically approach the negative real line, and where the oscillations will be very extreme. Okay, so the basic idea is if you deviate from in an angular direction from the positive real line, you should expect that your oscillations will be higher, okay, overshoot will be higher, and peak time will be higher. Okay, so in that sense, there should be, of course, some sort of loss of transient performance. Okay, so what about settling time? Okay, so if you remember, when we are discretizing a system from continuous to discrete time domain, the poles are mapped in this form, right? E to the power t, like sp is equal to z, right? Zp. So this is a pole in S domain, and this is a pole in Z domain. Okay, so this is the mapping of the poles. And the good thing is the poles, even if there are some differences when we do this mapping, they will share some of the transient performance characteristics. Okay, so moreover, we know that this is not an one-to-one onto mapping, but if we limit to the real line, okay, so e to the power t sigma, it will be equal to z, right? Okay, and this mapping, okay, so mapping of real line on the z plane is one-to-one and onto. Okay, and we know that this sigma, okay, defines the settling time, convergence speed in continuous time domain, and magnitude of the z defines the convergence time and settling time in the z domain. So what we can do is we can do an inverse mapping such that we can compute sigma in this form ln z bar divided by t, okay, which is the inverse mapping. So what we can do is we can technically convert these magnitudes in the z domain to real values in S domain, and then we can use the formula that we know from the continuous time systems course and compare the technical settling time. So if we do that, sigma 0.5, sigma 1, sigma 2 is equal to approximate, of course, there are some differences, minus 0.5, minus 0.5, minus 0.5. Okay, I think that's fantastic. So what it means that, so from a continuous time perspective, if we do reverse mapping, we will see that they will have the same real part, which will be 0.5, and we know that the setting time is equal to, if I remember correctly, I think the setting time is sigma divided by 4 for 2%. So the take-home message is these points, okay, they are technically located differently in terms of angular direction, and they're somewhat different located radial, but if we consider the sampling time, they technically has same setting time performance, and it is kind of consistent with respect to what we did here. Okay, so it means that if you want to compare or measure the setting time performance of a digital control system, because we have an actual system, we discretize it, so we still live in a real-time domain, continuous time domain, even sample it, what you should do is, you should use this formula, okay, here, which is the inverse mapping. Okay, take the magnitude of the complex number, take the logarithm, divide by t, which is the sigma value, and then you can use this sigma to compute the setting time in continuous domain, and which will the formula that we will use to assess the setting time performance of a digital control system. And as you can see, setting time performance is same. Okay, so if we go to here, what we obtained is, we obtained that if we increase the sampling time, overshoot performance, peak time performance degrades, but setting time performance doesn't change. And as you can see, it is the same result obtained from an analytical perspective. Okay, that's good. Exactly, that's nice. So what I will do, okay, good. So of course, so what I will do, okay, I will show, okay, for both sampling times, which is, well, let's compute for the unit response. Good. Okay, that's nice. So now let's try to compare steady state performance for the same value, right? We can do that. Okay. So again, using the same k value. So let's look at the steady state performance. Okay. So first of all, as you can see, these are both type 1 systems. For unit step, error steady state is equal to 0 for all cases, so we don't have any information there. Perfect. So what we can do is we can compute unit ramp response as to states and compute them, where unit ramp is equal to r of k is equal to k times u of k. Okay, so if we compute the steady state error under this metric for all systems, we will see that E 0.5 is equal to 1 over 2, E1 is equal to 1 over 2. I really recommend you to do the computations by yourself. E2 is equal to 1 over 2. Okay, so similar to the steady state performance, we can conclude that they're exactly the same, similar to setting time. Okay, so you can assume that if you keep the same controller, if you change the setting time, you lose some transient performance in terms of overshoot and peak time, but setting time as well as the steady state performance is same. Okay, but it's wrong. Okay, so we did the same mistake. Okay, so what we did is we evaluated the steady state error with respect to Rk. Okay, so why it's bad, I will show you. Okay, here, let's plot Rk for t is equal to, for example, 2 seconds. Okay, so it starts from 0. That's good. Okay, at 2 seconds, k is equal to 1. Like this is 1. This is 2, right? K is equal to 1, so it is equal to 1. Let's say this is equal to 1. Okay, at 4, it's 3. 4, k is equal to 2. So 2 square, it's equal to 4, right? Okay, so it's equal to 4. That's good, right? Okay, that's nice. So this is equal to, so it's not very nice. Okay, so it's, you get the point. I didn't draw it nicely. So now let's make it t is equal to 1. Okay, at 1, it is equal to 1. Okay, so it's kind of different, right? Okay, at 2, it is equal to 4. Okay, so if I actually measure this with respect to real time, I can see that the curve is steeper for lower sampling times. So it's not fair to compare them using the unit step input. So instead, what we need to do is we need to consider unit step in time domain and then convert it. So what we need to do is we need to do simply this. We need to look at the step response, unit ramp response, sorry for that, for R of t is equal to t, the actual ramp in time domain, and R of k is equal to technically k times t. Okay, so what we need to do is, in order to have fair comparison, we should also scale the input with sampling time. In that sense, if we compute error steady state, we will see that for 0.5, error for 1, error for 2 is equal to 1 over 4, 1 over 2, and 1. And obviously, steady state performance is better for the same gain for the lowest sampling time. Okay, it's good, right? I think everything's nice. So this implies that, so let's go to here. Okay, let's go to here. Okay, for same gain, k is equal to 2. Okay, so we are not changing the gain. Okay, overshoot decreases with sampling time. Okay, approximately. T peak time decreases with sampling time. Okay, so this is wrong, sampling time increases. So as we change the sampling time, overshoot decreases, peak time decreases, that's good. Okay, T setting time stays same. Okay, this is interesting. Okay, T sampling time, and error steady state, and of course for the ramp-like inputs, it also decreases, no, increases. Okay, so I think I made a mistake. Okay, let's clean that. Okay, so if I, okay, increase sampling time, percentage overshoot will increase, the performance will degrade. If I increase the sampling time, peak time will increase, which will reduce the performance. If I increase the sampling time, T setting time will not change. It will be same technically, approximate. There will be some small differences, but they're almost exactly the same. If I increase sampling time by keeping everything the same, we'll see that error steady state will also increase. Okay, so in general, if we just ignore the sampling time, no setting time, in order to improve the transient performance and also steady state performance, higher sampling time is better. Okay, and for this reason, in digital control systems, we really give a huge importance to the sampling time. It's being like constant as best as possible, and we would like to make it as small as possible. Okay, for example, in modern control system, in general, we want it to be 0.1 millisecond. Okay, sometimes it can be higher depending on your plant, but in general, we really want it to be as small as possible to have a good performance in real time. Okay, good. So now I will analyze a different point. Okay, that's good. I will analyze a different point. Okay, so let's compare the points where all Root-Locus has a critically damped location. Okay, so in this case, we have a double root. It's critical damped. Critical damp definition is same. Okay, so what is the idea of this point? We can compare them. Okay, so the gains are different. Okay, as you can see, 0.12, 0.25, and in here 0.46. The location of the poles are different, as you can see, Z is here. Okay, that's good. So why this point is good? Why this point is bad? So it's good because it's critical damped, which will expect the best transient performance. Okay, it's bad because, as you can see, gain is very little, very small, which means that we will get a bad performance in terms of a different location. For example, k is equal to 2. But maybe if we compare critical damp locations, we can get a different results. Okay, good. So what we will do is let's look at the overshoot. 0, right? Okay, because it's critical damped. If we pick a critical damped location, of course, if you change the sampling time, nothing will change. Okay. Similarly, T peak time is just redundant. You don't even talk about it. Okay. So what about settling time? Okay. So if you remember, in order to compute settling time, what we will do is we will do this formula. Okay, ln z divided by. Okay, what was the result? Okay, so let's remember, is it here? Okay, it should be there. Okay, okay, divide. That's nice. So we compute ln z divided by, okay, 0.5, something like that. Okay, done. Okay, so ln z divided by, of course, t. Okay, so t is sigma 0.5, sigma 1, and sigma 2. If I compute them, I will see that they're both equal to 0.5, minus 0.5, minus 0.5, minus 0.5. It's obvious because, as you can see, this is a perfect radius. Okay, the magnitude here, the radial magnitude, is same with the magnitude k is equal to 2. Okay, since I'm picking the same locations in both cases, of course I should expect the same settling time with k is equal to 2 value. Okay, so settling time performances should be similar to this, such that in actual time, settling time is equal to approximately 9 to 9 seconds. Okay, that's good. So I think we are doing good, because so if when I was comparing these points, like the points where response is critical damped, okay, no overshoot, peak time is redundant, and settling time is same. It's not changing. Okay, so I'm not losing anything currently with respect to different root-locuses. Okay, so if I compute errors 0.5, error 1, and error 2, when r of t is equal to t and r of k is equal to k times t, so it's a fair comparison, I will see that they're approximately equal to 4. Okay, so it means that they are same. I think it's quite interesting. Okay, so the take-home messages, when we compare root-locuses, where we keep everything fixed, including the gain, okay, so we generally obtain better performance results with lower sampling time value. But if we limit ourselves to the case where the root-locus is technically critical damped at this location, for this system, when we change the settling time, nothing changes. Almost nothing changes between the performance results. So this means that the comparing root-locuses when you change the sampling time is quite complicated. It's more complicated than the comparing root-locus plot in continuous time domain. Okay, so can you say that changing sampling time doesn't change anything? It's not, because as you can see, error statistic is 4. So in terms of percentages, now we cannot really measure percentages. It's a large number. It's not acceptable. Okay, so if you need to also improve the statistical performance, which is of course, then you technically have to await from this point, and at that time, when you become oscillatory, as soon as you become oscillatory, you start losing performance when you change sampling, increase sampling time. So first of all, we know that in terms of gain margin, lower sampling time is better. In terms of overshoot in general, as soon as you are oscillatory, the lower sampling time is better. In terms of peak time, it's better. In terms of settling time, they may be very similar to each other with respect to the actual system. It's generally the case, but we know that the other metrics also very important.